All right, students, so we have finally finished our unit on the scientific method. So from talking about observations and inferences to conclusions and abstracts, we finally made it. So in this video, I want to review all of what we've learned. I'm about to post a test for it, or an assessment, whatever word you want to use for it, on the scientific method, and I want you guys to do well. So let's start. We're going to go through the whole scientific method, and I'm going to lay out some of the important parts that we've learned. So, starting with observations and inferences. What is an observation? An observation is something that you take in about, or it's information you take in from the environment using any of your 5 senses. So, sight, hearing, smell, taste, touch. Those are our 5 senses. So if you touch something, see something, smell something, etc., these are all observations that we make about the world. An inference is something that we can conclude from having those observations. So if I smell chicken, I can make the inference that somebody's making chicken or somebody's eating chicken. Now, I might not be able to see that person. I'm only smelling. And then I can open my eyes and see the person making chicken, and so the inference is something that you can conclude based on your observations. Your observations are it's the information that you are able to get through your 5 senses. So the data that you collect in your experiment, that's observations. Not only do experiments start with observations about the world and make you curious, so it's the very first part of the scientific method, it's observations, but it's also a part of data collection, because that data you're collecting, that's observations. You're using a scientific tool and you're looking at what the tool says. Looking and getting information through that is observation. So you'll have observations while you're collecting data, but it's also the very, very first part of the scientific method, is forming observations about the world. Okay, and it's always better when you are collecting data to have as many observations as you can have. So why is it better? So it's like, why do we do more trials? It's the same thing. More trials is more observations. It gives us, it makes the inferences easier to conclude the more observations that you have. So let's say, using the chicken example, I smell chicken. What if I not only smell it, but I see someone making it? Well, then the inference that the chicken's being made by that person is a lot easier to conclude. So the more observations you have, the better. And okay, yes, and observations are data. So moving on to questions. Our scientific questions, they need to be 3 important things. You remember? They have to be testable, they have to be measurable, and they cannot be based on values or opinions. If you're asking a question like, what is the meaning of life? This doesn't work because it calls on values or opinions to answer it. Or what is nicer, bunnies or cats? This also calls on values or opinions. Your opinion is that, a bunny is nicer or a cat is nicer. You cannot do a scientific experiment based on opinions. So that was what you need to keep in mind. Something that I saw a lot of you make mistakes on is when I asked for a scientific question, you'd give me a research question, not a question that you could do an experiment on. So for example, how do volcanoes explode? This is not a scientific question in the sense of like an experimental question. It's not something you can do an experiment on. It's something that you're researching, and you can see what the world has to say about that. But you can't make a volcano explode on your own. You can maybe make a model of one, but you cannot make a volcano explode. So unfortunately, that's not a scientific question. It's something you can research and look on your computer and see what other people have to say, but you can't do an experiment on it. So when you're making a scientific question, you have to be able to do an experiment on it. That means it's testable. And measurable means you can use a scientific tool to answer or to do the experiment. Whether it's a thermometer, ruler, whatever, that's what measurable means. So if you say, how do earthquakes happen? Why do we have tides in the ocean? Like, those are good questions, and it's great that you're curious, but these aren't things that you can do experiments on. So when I ask for a scientific question, that's what I mean, and that's what a scientific question is. It's measurable, testable, and has no values or opinions. The next part is forming a hypothesis. So after you form your question, you have to form a hypothesis. First and foremost, a hypothesis is a prediction of what you think is going to happen in your experiment. Many of you would write an if-then statement, but tell me nothing about what you think is going to happen in your experiment. This is unacceptable because a hypothesis is supposed to tell you what you think is going to happen. And that is the purpose of a hypothesis. It's to say what you think, what you expect to happen. First and foremost, that's what's important. It is a prediction. It's based off previous knowledge. So you might have heard educated guess or something like that. That is referring to a hypothesis because it's educated, meaning you have previous knowledge and you are able to make a prediction of what's going to happen based on your previous knowledge and things that you've seen before. So that's a hypothesis. It's a prediction. Now, if-then statements. You can put your hypothesis into an if-then statement. Many of you would use an if-then statement, but then wouldn't tell me a prediction. That's not a hypothesis, that's just an if-then statement. I'd much rather you tell me what you think is going to happen, give me a prediction, than give me an if-then statement without a prediction. So, remember, hypothesis is a prediction of what you think will happen in your experiment. Now, moving forward is the procedures. The procedures, also on the prediction, a prediction answers your scientific question. So back to hypothesis. If your hypothesis doesn't give an answer to your scientific question, you did it wrong. So it should give the answer to it, or what you think the answer is, before you even do your experiment. Okay, now moving on to procedures. Procedures, in this part of the scientific method, you identify your independent and dependent variables. What's the difference between those? An independent variable is the cause, dependent variable is the effect. That's the way to think of it. Independent cause, dependent is the effect. Also, you could think of it as the independent variable is the thing that you have control over as the scientist. You can control the independent variable. It's independent. If you ever think of, everyone says strong, independent woman, it means she can do everything on her own. She doesn't need anyone else to be able to do the things in her life. Independent means you do not need other things to make this happen. So that your independent variable is the part of the experiment that you control. It doesn't need the dependent variable to work. So maybe that helps you think of it. The dependent variable needs the independent variable. It's the part of the experiment that you're looking for. You don't know. The independent variable is the part of the experiment that you don't know what's going to happen until you do your experiment. It's the thing that you're measuring. So there's a few ways to think of that between an independent and dependent variable. If you still don't get it, rewind, listen to that again, because that's an important part of understanding science. Okay, and also you could rewatch the video on independent and dependent variables. That could be helpful. Now moving on to control group. The control group is the part of the experiment that you do not apply your independent variable to. So, if you are doing how does fertilizer affect plant growth, and you put fertilizer in all of these different plants, the part of the experiment that you don't add any fertilizer to, that is your control group, because adding fertilizer is your independent variable, and there's one pot that you're not adding fertilizer to, so that's the control group. Some of your experiments will not have a control group. Most of them will, so keep that in mind. If you're concerned about if you have one or not, you can email me, let me know your concern, but that's that. Now, procedures, another part of procedures is you need to make a numbered list. That is a list of exactly what you did in your experiment or what you're planning to do, and then you do that. And it's helpful for other scientists if they want to repeat your experiment. Okay, so we've done observations, questions, hypothesis, procedures. Now moving on to data collection. So data collection, there are two types of data. There's qualitative and quantitative. Quantitative is numbers, quantity, quantitative. That is the kind of data that we're looking for in your experiment. And then qualitative is data that's not numbers. So if something sinks or floats, or if, I don't know, data that's not numbers, anything that's not numbers, color changes, pH changes. Well, pH you can measure, but it's also something that you can tell by color. If you don't know what pH is, that's okay. Now, that's the difference between qualitative and quantitative. You want quantitative data, data with numbers. Then we talked about data tables when we talked about data collection. When you're setting up a data table, so this is your table, on the right column, we have what? The independent or dependent variable. You have the independent variable on the right column, and then on the left, you have the dependent variable. Also, when you are forming or collecting data, you will have multiple trials. We do this to solidify your data. Like I said, the more observations you have, the easier it is to make an inference. So that's why we do multiple trials. It makes it easier to form conclusions, to make inferences based on the data that you've collected. So you guys will do 3. Some of you might be doing 2. If you did, that you've contacted me, maybe you're doing 4 or 5. Good for you, if you're doing that. Now moving on to data analysis. So this is where you'll have graphs, and you might do a bar graph or a line graph. A line graph tracks progression if something's changing over time. It's also, if time's involved, and unless your time, if time is your dependent variable, like for the Skittles experiment, that's a bar graph. But if time is you're tracking how something changes over time, that's a line graph. If you don't know if you're supposed to do a bar graph or a line graph for your experiment, you can come and ask me and I'll help you out and help you think through that. And then the X and Y axis. The X axis is the horizontal one, and the Y axis is the vertical one. And, well, I should do it this way, so the X axis has your independent variable, and your Y axis has your dependent variable. So X axis is the thing that you have control over, and Y axis is the thing you're measuring, the results. What you did not expect to happen is your Y axis. Now, then in the data analysis, you write a written data analysis. You say, fertilizer affected plant growth in that the plant that was given the most fertilizer grew the tallest. And you'd say sentences like that. All of the details of how to exactly write a data analysis is in the data analysis video, and there are numbered steps that will help you. So you'd have a few sentences or 1 or 2 sentences for each of those steps. Okay, then you move on to conclusion. The conclusion is a 3-paragraph part of your experiment, and the details of that, what's in paragraph 1, what's in paragraph 2, what's in paragraph 3, it's all in that video, so check that video if you do not know. It's important because you'll need to write one for your own science experiment. So yes, review those 6 steps and go back and look because you will have to write one for yourself. Now, then we wrote an abstract. This is not a part of the scientific method, but it's part of when you're writing a report yourself, you'll have to write an abstract, which is a summary of your entire experiment. Now, let's say you do your whole experiment and everything looks good and everything, then another scientist comes along and is like, I disagree. I'm going to try it on my own. And then they try it, and maybe they disagree, maybe they don't. In science, even when things are tested over and over and over again, and you can get the same results over and over and over again, some scientists might still disagree. So that is just a part of the scientific method. So they would form a new hypothesis and make new experiments, or they might do your experiment and do that one over again, and maybe they get different results. And they might disagree because they think this is not happening because of the reason you think. It's happening because something else. And they would try a new experiment. So Even if experiments are repeated and get the same results, you might not have agreement in the science world. So that is all for review of the scientific method. If you have questions, let me know. Go ahead and take that assessment. It might look a little different from other things we've done in the past, because I'll have you read about some experiments and then tell me what part is data collection, what part is the hypothesis, questions like that. If you don't understand anything about the scientific method at this point, I don't know, you can of course reach out to me, and I would love to have a Zoom call with you. But yes, you guys should be experts at this now, so good luck to you.